Okay, so we are back at it after a long pause. So without any further delay, let's just start. So this is the result that we saw in the last video. What it says is that it gives us another condition, another equivalent condition for a linear operator to be regular. I say another one because this does not involve minimal polynomial. Instead, it says that if our vector space is finite dimensional over the field over which it's a vector space, then any linear operator T on the vector space is regular if and only if T is an onto function, if T maps V onto V. If and only if, actually, it's an equivalent condition for regularity of T. Onto-ness is equivalent to regularity. So let's see the proof. So we have to prove two implications. Let us first suppose that T is regular and prove that it's onto. Let T be regular. It means that T is invertible, so there is an inverse, a two-sided inverse of T. Now, we already know that the image of V under T is a subspace of V simply because T maps V into V, but we want to prove that it's onto V, which means that we have to prove the reverse inclusion as well. That is, we need to show that V is also a subspace of Vt. So for that, let V be any vector in V. Then V can be written as V1, where 1 is the identity operator, which is also the unit element in this algebra. And because T is regular, this identity operator can be written as T inverse T, and when you apply this product on the vector V, this just simply means that first you apply T inverse on V and then on the result you apply T. But then what do we see here? We see that this arbitrary vector V coming from our vector space is actually the T image of some vector, and this some vector in this case is Vt inverse, which is some vector again in our vector space V. And because of this form that now V has, this belongs to the image of V, or in other words, the range of T. So any vector in V is also in the range of T. Hence, we have the other inclusion as well. Now you combine these two containments, two inclusions, and get equality. But that just means that T maps V onto V. That is, T is onto or surjective. So we have proved that onto-ness is a consequence of regularity. Now we need to prove the converse. But instead of proving the converse itself, that is, instead of assuming that T is onto and proving that T is regular, we will rather prove the contrapositive of the converse. That is, we will assume now that T is not regular and prove that it is then not onto. Okay, so let's do that. Conversely, let T be not regular, i.e., T is singular. T is a singular linear operator. Then we recall one result that whenever that happens, then there is at least one non-zero vector in our vector space that T maps onto the zero vector. This is always true when T is singular, and that result is, I think, theorem 613. This is 614, so the previous theorem. By theorem 613, Vt is equal to 0 for some non-zero vector V in the vector space V. Of course, the zero vector is mapped by T onto the zero vector. There is nothing surprising about that. But if T is singular, then there is at least one non-zero vector which is also mapped by T onto the zero vector. Well, let us call this V1 because we are going to find this as an element in a list of some possibly other vectors. So you see, now you recall one result from the fourth chapter, that is on vector spaces, where we have already seen that in any vector space, if you have any finite dimensional vector space, of course, that's what we have here. If you have a non-zero vector, then you can extend this non-zero vector by including possibly some other non-zero vectors to a basis of the entire space. And this was lemma 425. Now, that is, you can enlarge the singleton set consisting of V1 by including some other vectors if they are needed, so that the enlarged set, the superset, is a basis of the entire space. By lemma 425, V has a basis of the form of this form. Vn, where of course n is the dimension of V. If you want, you can write here dim f as a suffix to emphasize that f is the underlying field, but that is understood because f is the only field in this situation. Okay, so we need not, if there is no need to write that separately. Okay. Now, this implies what? This implies that every vector in V is a linear combination of these basis vectors, because that's what a basis does. And that in particular implies that the range of T, that is Vt, also is spanned by some vectors. Let me show you what I am talking about here. Now Vt is equal to the linear span of this set By the way, why? Exactly why is it true? Let's see why this is true. You take any element in Vt, how will it look? It will be of the form Vt, where V belongs to V. Now because V belongs to V and this is the basis for V, V will be a linear combination of these basis vectors. For some scalars coming from the field. So now if we apply the operator T on this expression, on this linear combination, then Vt will be this. Vn, alpha n Vn. Class, let me write it here. On this you apply T. Because T is linear, so it respects addition and scalar multiplication. So you have this. So what does this tell you ultimately? It tells us that Vt is a linear combination of V1t, V2t and so on up to Vnt. Or in other words, that these vectors span the range Vt. That's what we have written. Vt is their linear span. Okay. So now exactly how many vectors are spanning Vt? That is the question now. Although we see a list of n symbols here, but we don't really know whether these VITs are all distinct. They may not be. These are distinct due to linear independence. A consequence of linear independence is that these are distinct vectors. So we have, you see n distinct vectors here. However, here you may not have n distinct vectors, there may be repetitions, who knows. And in particular, there is one very special vector among these vectors, which is V1t, and that V1t is 0. Since V1t is equal to 0, we see that Vt is also spanned by these the remaining vectors. And that is why, now you see, we are able to discard this V1t, that's because it is 0. So in a span, 0 has no effect. The other vectors, of course, will continue to span Vt. Now, among these other vectors also there may be repetitions, we don't know. But the list of symbols that you now have, it has n minus 1 symbols. They may be distinct, may not be distinct, or in other words, they may form a linearly independent set, may not form a linearly independent set. Whatever the case is, the dimension of Vt is less than or equal to n minus 1, because these n minus 1 vectors, whether they are or are not linearly independent, are spanning Vt, the subspace Vt, the range. So the dimension, of course, will be at most n minus 1. However, n minus 1 is obviously less than n. And n is the dimension of V. Well, here while explaining this thing, I should not have said, I should not have emphasized so much on distinctness, but rather on linear independence or dependence. But anyway, you understood why we have this. And this is less than n, which is the dimension of V. So it means that Vt, of course, it's a subspace of V, but it's a subspace of V whose dimension is less than that of V. So of course Vt cannot be equal to V. It's a proper subspace of V. Hence, Vt is a proper subspace of V, but then T is not onto, T does not map V onto V. And this is in fact the contrapositive of the converse, because we have proved that if T is not regular, then T is not onto. Or in other words, if T is onto, then it has to be regular. That was the converse. So this completes the proof. All right. Okay. Now, this is a new equivalent condition for regularity of a linear operator. New means it does not use the minimal polynomial of the operator, which is also there. I mean, if you recall, a linear operator is regular if and only if the constant term of the minimal polynomial is non-zero. So we have already come across that. That is another condition, but this is another condition. Now we can change this condition slightly even more. I mean, onto-ness is equivalent to regularity, but still we can say something else in place of onto-ness. Let V be finite dimensional over F and T be a linear operator on V. So just now we have proved that if T is, or okay, why should I write only 1/2 of the result? T is regular if and only if Vt is equal to V. Okay, so we are just restating what we have done. but Vt is equal to V if and only if dimension of Vt is equal to dimension of V. Okay, how is this last line true? Well, if two finite dimensional vector spaces are actually the same, then of course their dimensions also are the same. But what about the converse? Suppose the dimension of Vt is equal to the dimension of V. Does that also imply that Vt is equal to V? Well, in general, it does not exactly imply equality but isomorphism, but here the situation is somewhat special. Vt and V are not arbitrary vector spaces. Already Vt is a subspace of V, and if you recall a previous result from vector space theory, that says that in a finite dimensional vector space, the dimension of any proper subspace is strictly less than the dimension of the original space, which means that if a subspace has the same dimension as the original space, then it cannot be a proper subspace. It has to actually be equal to the entire space. So that's why finite dimensionality of V and this containment implies that if we have the dimensions equal, then the spaces are also equal. So that means we have got another equivalent condition for regularity of T. T is regular if and only if the dimension of its range is equal to the dimension of the space on which it's a linear operator. And this quantity is of importance not only because it gives us another way of stating this same result, but it also is kind of a measure of regularity, or you can also say a measure of lack of regularity or singularity of a linear operator. You see, what is the dimension of Vt? After all, it's a non-negative integer, right? And in the present situation, in this current situation, the largest possible value of this dimension of Vt is dimension of V, and that happens precisely when T is regular. So when this quantity is the largest possible, when T is regular. And if it is not the largest possible, if it becomes less than the dimension of V, then T is not regular, T is singular. But even then, depending on how large it is, T is that far from being as singular as it can possibly be. It may be a little confusing to see what this means, but let me show you the other extreme. This is the one extreme value of this dimension of Vt. However, because it's the dimension of a subspace, it can also be 0. That is the smallest value it can have. If the dimension of Vt is 0, then Vt is the 0 subspace of V, because only the 0 space has 0 dimension. It's as good as a point, just like a one-dimensional space in some sense can be thought of as a line, something like that. It's just like a point. So Vt is equal to 0. But you see, what is Vt? Vt is the range of T. It consists of the images of all the vectors of V under T, and that is 0, which means that T sends every vector of V onto 0. Or in other words, T is the 0 operator. It's the zero transformation. So in this case, t is equal to 0. And this is extreme singularity in some sense. Okay, it's not anything precise or mathematical, but in some sense t is as singular as it can possibly be. It is singularly sending all the vectors onto 0. On the other extreme, in this case t is regular, and regularity also means that t only sends the 0 vector to 0. No non-zero vector is sent by t onto 0. Okay, so if singularity means sending things or collapsing the vectors onto the 0 vector, then this is as far from being singular as it can possibly be. In other words, it's not singular at all, but this is as singular as it can possibly be. Okay, so in that sense, this is a measure of the degree of singularity of t. Because of this, it has been given a name also. And you already know this name. This is the next definition. This dimension is called the rank of the linear operator t. You may be more familiar with rank of a matrix. Those things are also coming. In the third section, we will see how matrices are related to linear operators. Let V be finite dimensional over F and T be a linear operator on V. The rank of T denoted by R of T is defined to be the dimension of the range of T over F, of course, that is understood, it's there in the background. That is, R of T is the dimension of the range of T. Note carefully that we have defined it only for finite dimensional vector spaces V, so that Vt being a subspace of V is also finite dimensional, and as a result you are always going to get a non-negative integer here. However, in one of the exercise problems, we will have an occasion to do this thing for infinite dimensional V also. So we will mention it then, okay, in the exercise solution. But right now, for us, rank is only defined for linear operators on finite dimensional vector spaces. Now this rank, note that this rank actually is the function itself, whose domain is the algebra of operators, and the codomain or range, whatever you want to call it, depending on how it has been named, is the set of integers, or you can also consider the set of non-negative integers. Okay. Now let us now see some properties of this function. So the next lemma is about that. What kind of properties does the rank function have? This will be lemma 613. Okay. If V is finite dimensional over F, then for linear operators S and T on V, these inequalities are true. The rank of ST, the rank of the product, because you see, we are in an algebra, so we can take the product of two algebra elements. In our particular case, this just means the composition of the operators S and T. This is less than or equal to the rank of T. This is one inequality. Then number 2, the rank of ST, it has been instead given like this. Rank of TS is also less than or equal to the rank of T. Well, if you write ST here, you should write S here, but let me just write whatever is there in the text. And so, combining these two things, we also get this. Rank of ST is less than or equal to the minimum of the rank of S and the rank of T. And there is a third one also. Rank of ST is equal to rank of TS is equal to the rank of T if the operator S is regular. So let's now prove these things. The first inequality is extremely easy, it's almost immediate. Proof. Number 1. Okay, so we need ST. Since Vs is a subspace of V, because S after all maps V into V. So we have V ST, which is Vst by the definition of composition, and this is a subspace of Vt. Why? That's because when you apply the operator T on these two sets, direct images preserve containment. This is a property of functions in general. So from that we have this. So you see that the subspace VST is contained in the subspace VT, or in other words, VST is a subspace of VT. So of course its dimension will be less than or equal to the dimension of this. So, but what is its dimension? Its dimension by definition is the rank of ST. This is less than or equal to the dimension of the range of T, which by definition is the rank of T. So that's how you have R of ST less than or equal to R of T. Okay, so that is the first one. For the second one, we have a slightly different thing. We have Ts here and we still have T here. So in this case, we are going to consider this first. Let M be R of T. M is R of T means the range of T is M dimensional. So the range of T has a basis consisting of some M vectors, M number of vectors. Well, actually, to avoid a slight confusion, instead of straight away going like this, you can dispose of one trivial case first. If M is equal to 0, because many people will ignore these cases, but which may cause confusion. Okay, M can be 0 also. If M is 0, then rank is 0. What does that mean? Rank is 0 means the range of T is the 0 subspace because it is 0 dimensional, and in that case T itself is 0. So we just straight away directly write, if M is 0, then T is the 0 operator. In this case, okay, in this case what happens to this inequality? In this case the inequality simply becomes equality, because R of Ts is, since T is 0, this is the 0 operator, so its rank is 0, and R of T again, this is also 0. So we have equality, which means this is still true. So now we can consider the case M greater than or equal to 1, because M equal to 0 has been handled here. Okay, so now there is no confusion in considering a basis having M elements. Now Vt has a basis consisting of M elements. Then Vts equal to Vt S is the linear span of these vectors. To see how you recall an argument that we saw in this video itself, where we had one basis of V. I mean, in that case we had a basis of V consisting of V1, V2 up to Vn, and we then concluded that the range of T, Vt, is spanned by V1T, V2T, that thing. Okay, so it is exactly like that, where in this case, in place of V there, now you have Vt, and in place of the operator T, you have S. Same argument. Okay, so we have this. But again you are looking at a list of M symbols, M vectors, which may not be distinct. So what does that mean? It means that whether they form a linearly independent set or not, the dimension of Vts, because the linear span of these vectors is Vts, so the dimension of Vts is at most M. It may be less than M also. So the dimension of V Ts is at most M. However, by definition, what is this dimension? This dimension is the range of Ts, and M is just the range of T, I mean the rank of T, rank of Ts, sorry, not range. So this is your second inequality. R of Ts is less than or equal to R of T. Combining parts 1 and 2, we get what was it, R of St or Ts? St. It actually we can take Ts also, but let's just take St because that's how it was stated. So R of St by part 1, this is less than or equal to R of T, and by part 2, R of St is less than or equal to R of S. In fact, precisely this is not given in part 2. Instead, we have R of Ts. R of Ts less than or equal to T, but we switch the roles of S and T and you get this. So, R of St, because it's less than or equal to both of them, it is less than or equal to their minimum. And now we finally prove the third one. The third one is an equation, it's an equality, where we have the extra condition that S is regular. Since S is regular by theorem 614, S is onto, i.e. Vs is equal to V. So Vst equal to Vst, because Vs is V, this is just Vt. Hence, the rank of St, which is the dimension of the range of St, is also equal to the dimension of the range of T, so that is equal to the rank of T. So we have proved that the ranks of St and T are the same, but now we need to prove that the rank of Ts is also equal to the rank of T. For that, the approach is exactly like this. That is, so you see, again we are going to consider that, say, R of T is M. Okay, so instead of writing everything in detail, let me just show the steps. M is R of T. Again you start like this. If M is 0, then T is 0. But if T is 0, then R of Ts and R of T are both equal to 0, but anyway they are equal. So that is one case. And then you consider this. So let me just basically repeat this. Then Vt, because M is the rank of T, so Vt has this basis consisting of m linearly independent vectors. Alright. And then you again write this. So far it is the same, just like this one, exactly the same thing. However, this time, instead of simply getting an inequality, we are going to get an equality. And the reason is that besides spanning V of Ts, this is now a linearly independent set. And this linear independence, which in general may not be available, is now there because S is regular. But how? That's what the author also asks as a question to the reader. So additionally now, why are these vectors linearly independent? Let's see. So we can modify this part itself. For linear independence of a finite set, we just apply the definition. Suppose these are scalars such that this linear combination is 0. Okay, now because S is a linear operator, this means the S image of this linear excuse me, the S image of this linear combination of the W's is 0. The S image of this is the 0 vector. However, S is regular, so S has an inverse. So we can apply the inverse on both sides. Beta MWM S inverse, that is equal to the S inverse image of the 0 vector. which is 0, because S inverse is a linear operator as well, and it maps, any linear operator maps the 0 vector onto the 0 vector. But this is just what this becomes the identity operator, so you get this. However, this is a basis. Okay, so the W's are already linearly independent, and that's why all the betas must be 0. But then we have proved that these vectors are also linearly independent. So this time you are looking at not just a spanning set, but in fact a basis for VTS. This is a basis for the range of TS, and that's why the dimension of VTS this time is not less than or equal to, it is less than or equal to m, but more specifically actually it is equal to n, because there are m vectors which are spanning BTS, m distinct vectors, and this distinctness is a consequence of linear independence, and that is why the rank of TS is equal to n, which is the rank of T. So that's how the ranks of both ST and TS are equal to the rank of T if S is regular. And finally, there is a corollary. The corollary says this, that if instead of writing everything, it just basically says this: you have a finite dimensional vector space V over F, and S and T are again two linear operators on V. If S is regular, then T may or may not be regular. Then the rank of ST/S inverse, regularity allows us to have S inverse, is the same as the rank of T. The proof is a one-line proof. Recalling part 3 of the previous lemma, what does part 3 say? It says that rank of ST is equal to rank of TS is equal to rank of T. But we only need that first part where we can change the order of S and T. In place of ST, we can also take TS if S is regular. Well, here also S is regular. So you can consider S as one operator and TS inverse as another operator. So using that property, you can change the order. And in place of STS inverse, you can write TS inverse S. Okay, S, TS inverse S. So that is just R of T. And this completes the proof of the corollary and also the theory part of this section. So having completed this section, not fully, there are the exercises. The next we will see the exercises. And that's just it for tonight. So the next upload is this coming Saturday, and Saturday I think we have exercises from Lee's algebra and also from calculus by Thomas and Finney. So there won't be any video. We will see exercise solutions in the community section. So see you with that on Saturday. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.